Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a supplementary video to follow the video that I just put out on a summary of integration techniques. This is for Calc 2 students who really want to learn how to kind of incorporate all of those methods into a nice, clean, well, I don't want to say clean, but at least a tactic to approaching integration. So in this video, all I'm going to do is just go through 5 examples and we'll approach each of them by looking at how we could consider the different tactics and the ramifications of our choices. So if you look at this first integral, you can see that it is a very unique looking integral, and we're going to go ahead and list out some tactics here. The very first thing I'm going to note is that you cannot directly integrate that. I would normally list out all of the tactics and cross them out as I say that they're not going to be worthwhile to use. However, in this case, generally, we don't ever write direct integration because that rarely will work. However, let's go on to U substitution. Now, U substitution actually might be attractive here. You might be attracted to allowing U to equal maybe an x to the 1/3, or maybe that entire denominator. So because that's a possibility, I will leave it there as a tactic. The next one I generally consider, just as a quick view whether or not I should use it, would be the product of trig functions, or if it has trig functions. And the reality is this does not, but I'll still list it down here just for your benefit. Now, when I write trig functions like that, first of all, I always shorten the word functions to FNCS. And second of all, I'm only writing it for your benefit. I totally know this is not the product of trig functions, so I'll go ahead and cross it out. Another thing I want to mention about that is it doesn't actually have to be a product of trig functions. It could be like a sine cubed or something like that. So in other words, it's not a product of 2 different trig functions, but still, I consider that like a trig function integral. The next thing I'll think about is the possibility of this being maybe a trig substitution. And actually, this could possibly, after some strong modifications, be a trig sub. So I'll go ahead and write that down. I'm not going to cross it out. I'll just write it down. Again, that's only after really some heavy substitutions in here. So likelihood is that we're not going to do trig subs on this one specifically, but it's just there in our tactic list just in case. The next one, and notice these are all sort of like substitutions. The next one is going to be a radical substitution, which is a very specialized U substitution. In fact, most people would just probably call it a U substitution. A radical substitution is when you let U equal a radical. Again, it's just a very specialized U substitution. In this case, I probably would let U equal the cubed root of x because that would help out. Or maybe the square of the cubed root of x, who knows? But that's a consideration, a very strong consideration in fact. The next tactic I'll consider is partial fraction decomposition. I'm not going to cross that out because I can easily see that this is very quadratic in nature. And if a U substitution leads to a factorable denominator, then I know it's probably going to be some sort of partial fraction decomposition. So I'm not going to cross it out. However, I do know that it's not initially a partial fraction decomposition. I'm just going to leave that in that list just in case. And then finally, the tactic that I tend to save until the very last would be by parts. Now, my students are actually kind of selling me on using by parts earlier and earlier because some of my students are very savvy with by parts. They end up doing a lot of substitutions with by parts or integrations by parts, and it can be very, very beneficial. So at the end of this, I might retry this using by parts just to see, but the likelihood of it working with a by parts method is very low. Of the remaining good tactics, it's pretty much all of them. However, I know that, again, the partial fraction decomposition is going to be saved till later if it does work. Same thing with the trig sub. So really, I'm going to probably just start with a U substitution, or at least attempt one, because it looks like it might be advantageous. As far as U substitutions go, there is likely one really good way to do this and a couple really bad ways to do this. The way that I normally encourage people to do U substitutions is letting U equal kind of a large piece. However, that's not going to be wise here. For example, if you let U equal the entire denominator, then du, the differential of U, would be that mess right there. And to be honest with you, that will be very challenging to kind of rectify in this situation. So I probably don't want to use that large of a U substitution. Again, I'm really looking a few steps ahead here. Yeah, sure, that whole denominator would become a U. However, dx would be traded out for all of this business underneath du, and that is just not a good looking factor to deal with. So instead, I'm going to go ahead and cross this attempt out. That's an attempt that I don't think is worthwhile, but I will try a different U sub. Specifically, I'll try U equals this middle value right there, the x to the 1/3. Now, before I find out what du is, I should say that a lot of people, when they go through and they try different substitutions here, they might be wondering, why is he choosing U to be x to the 1/3? Why didn't he choose U to be x to the 2/3? It's because if U is equal to x to the 1/3, I can get x to the 2/3 very easily by squaring both sides. Using this type of U substitution and allowing U squared to be x to the 2/3 makes this a factorable trinomial. It becomes U squared plus 3u to the first plus 2. We totally know that factors, so that's a really nice substitution. Also, du looks kind of dangerous, right? It looks as though that du might be a bit of a mess. Don't forget the dx there. But it turns out that that can be written in terms of u. So let me just showcase that. So this shows me that the dx that we see in that numerator can be traded out for 3 x to the 2/3 du. Well, x to the 2/3 we know is u squared. So this is going to be really nice. We'll have a u squared in the numerator, we'll have a trinomial in the denominator. That actually is a really nice substitution. So this is the winner in my opinion. Again, dx, we'll trade that out right now. Before I continue, I just want to mention dx gets traded out for du, but our integral is now improper. That's not the right definition of what an improper integral is, but our integral is in poor form. How's that? Because it has a mixture of variables. We don't want that. So just to let you know, you cannot operate on this integral. You'll need to exchange that x to the 2/3 for some value of u before you can compute anything here. But that's okay. We're just writing some stuff in between. X to the 2/3 downstairs, well, that becomes a u squared plus 3 times x to the 1/3 becomes a u plus 2. And now I'll go ahead and exchange that x to the 2/3 out for u squared. And here we have a beautiful integrand, all very nicely written. It's actually a ratio of polynomials, which tells me that partial fraction decomposition might be a really good choice. However, let's go ahead and reinvestigate all of our integration techniques, just in case. So we've done the u sub. By the way, don't think that once you do a u sub that you're done doing u substitutions. You might have to go back and do one again. However, in this case, I could see that our u substitution was very successful. We now have a polynomial divided by a polynomial. I moved the 3 out front, I hope you don't mind. We might be able to complete the square on the denominator if we really wanted to do a trig substitution. Or, well, radical substitution is now gone. I'll just go ahead and cross that out. There's no need to use that one. Or we could use partial fraction decomposition. However, if you're going to use partial fraction decomposition, remember, the degree of the numerator must be strictly less than the degree of the denominator. And if you take a look at what we are working with, they share the same degree. So because of that, if you're going to use partial fraction decomposition, you will have to do synthetic division or long division first. So let's go ahead and take a look at both possibilities. I'll just go and do partial fraction decomposition because I like it. So I'm going to grab this and move this over here for my partial fraction decomposition. And again, this is just an option. You don't actually have to do it this way. I need to get the numerator to have less the degree than the denominator. To do that, I'm going to do a little bit of long division. We could see u squared goes into u squared once, multiply back through the checker work, that'd be u squared plus 3u plus 2, and then you subtract all that statement, you'll get a negative 3u and a minus 2, and you're pretty much done with your long division because that's the remainder. And so we know the integrand, which is u squared divided by u squared plus 3u plus 2, can be rewritten as the quotient 1 plus the remainder over the divisor. And we now can use partial fraction decomposition on that second term in the integrand, this guy right here. So I'll break apart this integral into two pieces, 3 times the integral of 1 du plus 3, and actually what I'm going to do is factor the negative off of both of those terms in the numerator, so I'll say a minus 3, integral of 3u plus 2 divided by, and then because I think that partial fraction decomposition will be very nice here, I'll go ahead and factor that denominator. And there we go. Very, very nicely done so far. Obviously the first integral is super easy, right? That's just 3u minus 3 times. And now we're going to go ahead and say, well, that integral, which is 3u plus 2 divided by the quantity u plus 2 times the quantity u plus 1, can be written as some number over u plus 2 plus some different number over u plus 1 du. Now off to the side, I'll go ahead and just make the comparison. You would start with writing that equation. Now this equation should be true for any value of u except for -2 and -1, only because those cause division by 0. However, if you multiply both sides by the LCD, which I'll just quickly do, now I can say these statements are equivalent for every single value of u. And we will make strategic choices for u. Our strategic substitutions will be u equals -1, because that will turn off the factor right behind the a there. So when we do that, the left-hand side of our equation becomes -3 plus 2. The term with the a turns off, and we get b times -1 plus 2. That is, b is equal to -1. And then our next strategic substitution would be u is equal to a -2, again because that will turn off the term with the b. Allowing u equal to -2 on the left-hand side, we get -6 plus 2, which is -4. We get on the right-hand side a times -2 plus 1. And then again, the term with the b turns off. So it's very fast, at least in this situation, to find out what the coefficients, the numerators of the fractions are. So let's go ahead and insert those in here. A is 4, b is -1. And now we go ahead and integrate. Remember, we did not start in the world of u's, so let's go ahead and figure out what we did to get that u in there. Let's see, we have to crawl all the way back up until we find that u substitution right here. U is equal to x to the 1/3. So let's go ahead and insert those in. There we go. That is the antiderivative of the original function. Let's see, the antiderivative 1 over x to the 2/3 plus 3x to the 1/3 plus 2. Now I did mention that I was going to try 2 different directions with this just to see if it would work, just to entertain myself. I think that the video would be long enough already if I didn't do that, but why not? Just to show that you could possibly do this problem a couple different ways. If you try to do a trig sub here, you have to complete the square in that denominator. Now you can see The completed square you should have no questions on. That's pretty okay. But the problem is that when you complete the square, you end up getting some fractions in here, and a lot of people don't like working with fractions. Oh, I forgot my du. So that is something that you might have to contend with. 2 minus 9/4 is negative 1/4, so I might as well write that in there. But if you wanted to do this, you're more than welcome to. I see that it is a difference of squares in the denominator, so I know that this I would like to be something like the secant squared, in fact. But it won't be exactly the secant squared because I need to factor off a fourth here. So I want it to be a 1/4 secant squared. That way it's a 1/4 secant squared minus 1/4, and I could factor off the 1/4. I would have a secant squared minus 1, which is a tangent squared. Let's go ahead and take the square root of both sides here. And just if you haven't heard me say it until I'm blue in the face, you do not need the plus or minus here because the secant will absorb the plus or minus when you're taking the square root of both sides. Now let's go ahead and take the differentials of both sides. And pretty much we are ready to go. Well, I say pretty much, there's actually a little thing we have to worry about, the u squared upstairs. So let's go ahead and maybe adjust this statement so that I can get u squared by itself. And I'll just keep it with u by itself so that I'll square both sides when I need to. All right, let's substitute all that stuff in. The u squared in the numerator, well, that's going to be this business squared. So if you square that out, you get to that point right there. So that's u squared. I'm going to put parentheses around that because I need to remind myself that that's all one group of objects. And then du will be traded out for a 1/2, which I'm going to put out front, secant of theta, tangent of theta, d theta. And then in the denominator, we have, let's see, that u plus 3/2 being squared. Well, that's 1/4 secant squared. And we can factor out the 1/4 from the denominator. And I hope you forgive me when I say that denominator will be secant squared minus 1 now, so it's a tan squared. Now already, just comparing to the other side, this is a lot more work. Even though the other tactic involved partial fraction decomposition, this ends up being a lot more work. But still, fair to try. The tangent upstairs will cancel with the power of tangent downstairs. Otherwise, you can go ahead and distribute that secant through the numerator. And in fact, in that numerator, I'm going to go ahead and factor out a 1/4 out of all three of those terms in here. At this point, I'm betting that there are going to be some students that say, wait, what just happened? How did he get that secant cubed? Or how did he get a 6 on that secant squared? That was me factoring out a 1/4. How did he get the 3/2? That was just me factoring out a 1/4. So pause the video and do some arithmetic, and you'll see that actually I did okay. Everything's all right. I actually took my time with it just to make sure. With the exception that this should be a 9 secant of theta. Little things that you don't see until you take a moment to breathe. Now, I spent a few moments kind of looking through this problem, trying to figure out maybe the best tactic from this point forward. And I gotta tell you, this problem is a little bit of a pain. I'm gonna break this apart a little bit. Not a lot, but I'll break it apart a little bit here. Now, each of these pieces is actually its own very unique problem that you have to face. And again, this is just to let you know that if you get married to a method, if somebody just decides, I'm going to do trig subs, and you keep going and you force your way through it, you can get it done, but man, it's going to be a mess. Now, the first fraction here, I'm going to leave until later on. The second fraction, however, is going to be fairly simple. If you let v, because we already used the letter u, if we let v equal the tangent of theta, dv will steal away a secant squared of theta d theta, which we have right here. So that one's going to be very nice. On the other hand, the last integral, I'm going to write in terms of sines and cosines. Secant is 1 over cos, and tangent is sine over cos. So that ratio is actually just 1 over the sine, or in other words, the cosecant. And that integral we happen to know just from our previous work. So what I'll do is I'll just rewrite, maybe I'll put quotes around this so I don't have to rewrite that. And I'll write this as 6, negative 6 technically, natural log absolute value of v plus 9 natural log absolute value of cosecant of x. And I should say it's actually a negative 9 because when you do this integration, it's a negative natural log cosecant of x plus cotangent of x. This is a very, I don't want to say obscure, but it doesn't get used a lot, this integral. And by the way, these are thetas, not x's. And because of that, people will often get a little confused as to if it's positive or negative, something like that. But let's go ahead, and we're almost done. But now we have to deal with, I think, the hardest integral of all, the secant cubed divided by the tangent. In this case, I'm going to rewrite the secant cubed as 1 over the cosine cubed and the tangent as sine over the cosine. If you multiply both numerator and denominator by the cosine, you will get the following. And that is not a good looking integral either. However, it actually can be done. You just have to do a substitution. If we let w equal cosine of theta, dw will be the negative sine of theta d theta. Notice we don't have a sine of theta d, or at least a sine of theta upstairs. So I'm going to solve for d theta. And you get to this point right here. Now, I'm doing this full method because I often see students really just get glued to a method and they will not give up. And I'm just letting you know, if you see me do that, maybe it'll convince you to not do that. I don't want you to stick with a method that is so dirty like this. Look how clean the partial fraction decomposition is, but you have time invested in this so you think you have to continue. You don't. You could have given up at any point earlier and not erased your work, but at least said, I'm going to pause and go someplace else. All right. So you probably noticed that I traded out the v in the natural log there for the tangent of theta, which is what we let v equal. And I'll just finish out by saying, well, our substitution was w equals cosine of theta. I can write sine squared in terms of w's, or in terms of cosines, that is. And rather than rewrite all this ink, I'll just say that's 1 minus cosine squared of theta. That's what sine squared is. So that's going to be, and all this up here. This is just to convince you. I would have to go and do partial fraction decomposition. And so I'm not telling you that you shouldn't try secondary methods. What I am telling you is, don't get so glued to a method that you just continue with it. Yes, we could totally finish that out. I don't want to, because there's no need to. I would have given up, or not given up, I think that's the wrong phrase, but I would have pressed pause on this and said to myself, I need to try something else. Let me just go over and try a different tactic. When I got to maybe around here, to be honest with you, or maybe here, but at some point I would have said, you know what? Let me see if I could just try something easier. So always be willing to kind of change gears. All right, that's all I'm going to do with this example. Here's another integral. And I already pre-wrote all the tactics out that I usually consider. And I'll go through and cross out the ones that I know are not going to work. For example, partial fraction decomposition, I immediately am going to just cross out. It's worthless. It's also not a product of trig functions. That's worthless as well. It's also not going to be a trig substitution because there's no sum or difference of squares going on. So boom, that's gone as well. Now I'm down to just 2 basic methods, u subs or integration by parts. This is very interesting in that this is the one my students are starting to convince me to just tackle with by parts. Normally, I would tell my students, do a u sub here, then do by parts. But my students, on the other hand, are very much like, no, I'm just going to jump into by parts. So let's go ahead and see how both methods work. The method that I used to, and still to this day kind of recommend, is to do a u substitution at first, and then take a look at what you end up with, and if you have to, do by parts. I think the u substitution is somewhat obvious here. You're going to let u equal x to the 1/3, so that du steals away a 1/3 x to the negative 2/3 dx. And when you see that, you can easily see that our integrand does not have an x to the negative 2/3 dx to steal away. So I'll isolate that dx, and that's what I'm going to trade out the dx for, is the 3x to the 2/3 du. Let's go ahead and do that now. There we go. Our integral becomes 3 times the integral of x to the 2/3 du. That's what dx trades out for. And we have e to the u. But it should be somewhat obvious that u squared is going to be x to the 2/3. And now I know I'm going to have to use by parts. It's a product of a polynomial and an exponential function. If you have not seen what I'm about to do, it's a nice fast way to do integration by parts if you have the product of a polynomial and a trig function, or a polynomial and an exponential function. It doesn't work very well for a lot of other situations, but it definitely works beautifully for the products of polynomials and transcendental functions. How's that? Since normally with by parts we use this idea that the integral of u dv is equal to uv minus the integral of v du, and since we've already used the letter u in our substitution here, actually I think what I'll do is I'll quickly trade out that letter u for the letter w, just so that I can make my life a little bit easier. There we go. Now we can go ahead, and that was our w sub. Now we can go ahead and use that u and v as they're meant to be used. Our choice for u in our integrand is going to be w squared, because again, you can integrate both of those. You can integrate a w squared and you can integrate an e to the w. However, because you can integrate both, you're going to have to now choose what you're going to differentiate, and you always choose the piece that will eventually change forms. If you chose to differentiate w squared, its derivative would be 2w, and its derivative would be 2, and its derivative would be 0. Having chosen to differentiate w squared, obviously we're going to integrate e to the w. Normally I'd write a dw there, but there's really no need. The integral of e to the w is e to the w, is e to the w, is e to the w. Those are all the antiderivatives of each other. And then you work with diagonals. You're going to add the product of these two. You're going to subtract the product. Oops, that was supposed to be a different color. You're going to subtract the product of those two. You're going to add the product of those two. So this integral will become 3 times the quantity, a positive w squared e to the w, minus 2w e to the w, plus 2e to the w. And don't forget, there is actually a plus c on that, and you could distribute that 3 through if you wanted to. There's no real need. But now we have to change back into the world of x's. Luckily, w is just x to the 1/3. And that's it. I know my exponent got kind of off kilter there. Sorry about that. Anyhow, so that's how you could do that anti-differentiation if you had done a w sub first, or a substitution first, and then went by parts. However, if you're like my students who are pretty darn good at this stuff, then you would do just by parts. Now, I have to be honest with you, I had the best of intentions of doing the other way, like how my students do it, where I just do by parts from the get-go. And I even stated that at the beginning of this problem. However, when I started doing it, it did not work out. So maybe it's best that you do not just always dive into by parts from the get-go. It sort of works, but then it gets really, really ugly, just like the previous problem. And so I did what I would normally do if I'm doing any type of integration, is I would press pause and go to a different method, specifically the one that already works and was short. So anyhow, just letting you know, this is a great example. I challenge you, please try it just with by parts and try to make it as clean and short as this. You probably won't be able to do that. So just a heads up, that is going to be pretty much the only way you can do this. That whole trick of using by parts right from the get-go can work beautifully at times, but obviously this is not one of those times. All right, our next integral is this guy right here. And this one, again, I just pre-listed out all the tactics here. And I don't think a u sub is going to be very helpful. So I'm going to immediately cross that out. This is one of those rare times where a u sub just will not help. Also, trig functions will be helpful in a bit. I can easily look ahead and see that all I need to really do is square this out. I'll get a cosine squared. And so the trig, not subs, but trig functions, the tactics listed in that material is going to be very important at that point. And that will also mean that by parts will be very powerful as well. So I'll go ahead and keep the by parts because I know by parts is going to come into play because we'll have an e to the x times cosine of x. Partial fraction decomposition, heck no, that's not going to work there. Trig substitution is not going to work either. I can just easily see that just from looking at the integrand. So really, by parts is probably going to be the major method, and then the second major method will be trig functions, specifically products of trig functions or power reduction formulas. Let's go ahead and multiply this out. At this point, you have 3 different styles of integrals. And each of these you can label very quickly with the method of attack. For example, direct integration. I know that's going to be 1/2 e to the 2x. Very quick. By parts for this guy because it's the product of an exponential and a trig function. And that guy, I'm going to use a half angle identity to reduce the power. Some people call that the power reduction formula. So call it whatever you want. A rose by any other name is still but a rose. We get down to this, and by the way, you should notice I left a big old blank space there in that area in the center, this stuff right here, because that is the bigger part of this problem. Let's go ahead and run the outer parts. All right, so really this problem kind of boils down to just integrating by parts in the center there. And this is just a reminder of how that's done. Because you've already gone through this material, I get to do this pretty quickly, although there's not really, I mean, I'm sure there is a shortcut for this. I personally just don't know it, so I don't do it. And here's where I'm going to stop, because if you take a look at what our integral really was, it was 2 times the integral of e to the x cosine of x, so I might as well just leave it like that. So what is twice the integral of e to the x cosine of x? Well, it's e to the x sine of x plus e to the x cosine of x. So I'll just insert that in here. And don't forget, we have a plus c at the very end. And there you go. That's the antiderivative, hopefully. And I don't think there's anything we need to combine here. So we're done. So that is the only way you can actually do this problem that I can see offhand. All right, here we go with yet another problem, our second to last problem here. And this one should be somewhat obvious on how we're going to do it. A u substitution is going to be incredibly powerful. If you let u equal sine, it'll immediately steal away this cosine. So that is a really good substitution. If you want to, you could try to let u equal 1 plus sine to the 4th. However, keep in mind that if you let u equal this entire 1 plus sine to the 4th, du is going to be 4 sine to the 3rd of x times the cosine of x. And that is a problem because I don't have the 3rd power of sine in that numerator to steal away. So just a heads up, I did a quick kind of look ahead. If I'd done that u sub, that's not going to work. But at least the u sub for the sine will work perfectly. And usually if I see a u sub, I'll just jump right into that. So here I go. So we've done a u substitution here, u equals sine of x. There was actually a better u substitution we could have done if you were looking ahead. So let me just showcase, after I do one more substitution, I'm going to showcase what we could have done from the beginning. A lot of people will look at this problem, stare at it, and think, do I have to do partial fraction decomposition? And the answer there is heck no. This looks very, very close to something like 1 over 1 plus v squared. It looks really close to that. In fact, so close, I'm going to force it to be that. How do you force this integral to be this integral? Well, easily answered. If you rewrite this integral as the integral of u over 1 plus u squared squared du, you can see I'll just let v equal u squared. Notice that dv steals away a du and a u. Of course, I have to divide everything by 2, but that's okay. So when I do that, I'll get 1/2 integral of 1 over 1 plus v squared dv, and we know the antiderivative of 1 over 1 plus v squared is a tangent inverse of v. Resubstituting in for what v is equal to, and we didn't start in the world of u either, so that'll be a sine squared in there. Now that is not actually a unique substitution. In other words, this type of integral actually does occur quite often, and so you do need to start looking beyond a double substitution here and try for a single sub. So think, what would I have needed to take the derivative of to get rid of this entire numerator rather than just the cosine? And if you think about letting u not equal sine to the fourth, but instead a sine squared, you could take a look at this format, and if you could imagine erasing that entire numerator, it looks like a 1 over 1 plus something to the fourth, but anything to the fourth to me still looks like something squared. So it looks like a tan inverse formula. Since I would love that to be something squared, I'm going to say it's a sine squared squared, and I'm going to let u equal the sine squared of x. That substitution will leave me with the following differential. By bringing down the power of 2, that's now sine to the first, and by the chain rule, you're going to multiply that by the cosine of x, and then dx. And notice we have in our integral a dx sine of x cosine of x, just like we have a dx sine of x cosine of x here. And if you make that trade and divide both sides by 2, you'll get 1/2 integral of du over 1 plus, well, that was a sine to the fourth, which is a sine squared squared. So you get this. And the antiderivative of that is a tan inverse of u, and u was sine squared. And so we get back to the very same result, a little bit faster. So while I didn't go through all of my techniques or tactics over on the left-hand side there, what I really wanted to showcase is that you can start down a road like a u substitution and get really creative with those u substitutions. If you want to steal away that entire numerator, what do you have to take the derivative of? And that would be either a cosine squared or a sine squared. Anyhow, that's a really cool example, and you do see stuff like that a lot as you move forward. As our final example in this video, we're going to take a look at this integral right here, which is usually pretty tough for students. Let me just tell you that there was actually an example underneath this example that I removed because it was way too easy. And so now I just have the prime example I want to work with. How would you tackle this? A lot of students will stare at this and maybe think u substitution, which is exactly what you're going to be doing. However, what do you substitute in for u? That's the big question. Like if you were to let u equal, for example, this square root of x, du would need to steal away a 1 over 2 root x dx, and I don't have that, but I can still do it. The problem is writing that x to the 1/3 in terms of the square root of x. That's actually pretty difficult. So maybe you would choose a different tactic. What if I chose u to equal x to the 1/3? Well, we suffer from the same issue. Not that I can't rectify the situation that we have an x to the negative 2/3 there. That's okay, because I know what x to the positive 1/3 is. I could just say, well, u squared is x to the positive 2/3, so this would be a 1 over u squared. Fine, whatever. But still, my issue is I can't write the square root of x easily as an x to the 1/3. So I'm back to square one. Both u subs are pretty terrible. The trick to these styles of problems is factoring. First, rewrite everything with rational exponents. Then rewrite those exponents with a common denominator. Again, I want to just convince you, I'm facing an integral with a few radicals within it. My immediate reaction is I need to make a radical substitution. So the first thing I'm going to do is I'm going to just rewrite things in terms of rational exponents, and I'm going to take a look at, well, what are the ramifications of different types of substitutions? Again, I tried out u is equal to x to the 1/2. That tells me that du is 1 over 2 root x, which is the same thing as 1 over 2u, and that's okay. However, When I look at what I have remaining, while that would be a u, this right here is going to be very challenging to write in terms of u. So I threw out that substitution. The same thing for u equals x to the 1/3. If I tried that, again, I'd suffer from the same issue. So I then decided to write the exponents with common denominators and factor out the lowest power version of the exponent. And at this point, this is a good time to make a u substitution. And my u substitution is going to be for x to the 1/6 minus 1. Now, a lot of people don't like this substitution, but watch what happens when you let u equal x to the 1/6 minus 1. First of all, if I add 1 to both sides, I get this relation right here. Now, yes, I could totally take the differential of both sides as written, but I don't want to. I want to raise both sides to the 6th power. And that's because I would love to not work with rational exponents when I take derivatives. So when I take the derivative of the left-hand side, I get 6u plus 1 to the 5th. The derivative by the chain rule of the interior is just going to be 1 and then du. And the differential of the right-hand side is just dx. Now all I need to do is substitute that in to our integral. The dx gets traded out for a 6 times u plus 1 to the 5th du. That x to the 2/6 power. Well, here's x to the 1/6, so x to the 2/6 must be the square of that. And finally, x to the 1/6 minus 1, that was our original substitution. And when you get down to this, it's very pretty because you get that. Now you can multiply out that numerator, do some division, integrate, and sub in what we let u equal. Remember, u is equal to x to the 1/6 minus 1. So all of those u's are just going to be x to the 1/6 minus 1. That should feel somewhat new to you because it is a weird substitution, but the tactic is when you have these mixtures of radicals in a denominator as a sum or a difference, a good idea is just to find the common denominator of their fractional exponents, factor out the lowest powered version of that, and then let u be the term or the factor with the lowest power of that. And when you do that, you then isolate the x, raise both sides to whatever power is needed to get that rational exponent off of x, and then take the differential of both sides, substitute things in, you'll see some beautiful algebra happens, and integrate. In this instance, just like the last instance, I didn't really go through the laundry list of tactics because the initial form of the integral forced me into this path. That pretty much does it for this. There's not much I can say. When you're doing a review, I could do 1,000 different integrals, and if you feel shaky, you're just going to feel shaky. I just recommend that you do 1,000 integrals. All right, have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.